Thank you. Let me just organize here in just 1 second. Can you see my screen?
Yes, we can, thanks.
Okay, great. All right, thanks. Good morning, everyone. Thanks to the organizers for putting together the workshop. It's very nice to see that happening. So what I'm going to talk about today, it is some work that we've been doing on fast reservoir simulation, especially for hydrocarbon exploration and prediction, right? So basically, let me just, for a few slides, just introduce a little bit what we do here. And then I'll talk a little bit more about the machine learning algorithms that we are using, or the architecture that we are trying to come up with. First of all, so, models in general, in petroleum engineering can come in any life cycle of the petroleum exploration. Can come into the form of usually this is more like a educational division, basically, right? But can come from the exploration, from the development, production, and after you produce you deplete the reservoir, and that's basically what has been going on right now. You can store, sequester CO2 or store other things inside the subsurface, right? But all of these phases, they come up with the models. That in some ways they are really large-scale models, and what I mean by large-scale, meaning they really take up, a reservoir, a big reservoir simulation may take up hours, days, or weeks just to be simulated, and especially every single phase of this development, they add up a little bit of uncertainty into the model, right? And coming up with a strategy to reduce uncertainty is also expensive. So what I'll be talking about mostly in the next few slides, it is just this last, let me just do something here. Going to be talking about especially this last phase over here of this workflow, which is basically how we do flow simulation and production forecast. And especially taking into account a reservoir simulation strategy. What I'm really interested, it is basically putting together this idea of a real-time closed-loop reservoir management, right? Which is basically putting together in a single loop, acquiring the data and running a reservoir model or whatever model you have, optimizing the reservoir, and closing the loop here between data and control input into the reservoir. What I mean by input here, meaning how you're actually producing the wells, right? How you can, what kind of a flow information you're getting out of the wells. If you are producing at the 10,000 barrels, if you're producing 10,000 barrels of oil or water or gas, we want to optimize on that, right? And basically as well, where you're going to place wells into the reservoir. Right? And this closed loop, they are actually based upon several components, right? That we can need to fit together to actually start up the closed loop. One, it is the reservoir characterization, which I'm not going to talk about today, but basically how you incorporate petrophysics into the problem. The second one that requires, if you're really looking at the real time, how you do fast reservoir simulations. Right, and that's basically what I'm going to talk about in the next few slides, and as well, that what we never really think too much. It is that the drilling process as well, right? Where not necessarily where you're going to place those wells, but how you're going to drill the reservoir, so drill the well so that we can actually follow a path that give us a good quantity of potential oil in place. Right, and of course, this gives how you design well trajectories and so forth. So the idea, for me at least, is try to come up with something that is a real-time closed-loop reservoir management in that sense. And as I mentioned, comes with uncertainty, and usually in petroleum engineering, what we do, we just run multiple realizations of these models and come up with a statistical way of getting the production. Right? So in particular, I am interested mostly in reservoir simulation, which is a key component, at least in my design. Let me just close here one thing. So, and basically you can see here that, we want to manage this reservoir. We want to optimize net present value of this particular production, counting how many wells you can drill. If you want to drill horizontal wells, if you drill vertical wells, if you want to place wells here in the flank, or if you can place wells here on the bottom. So that gives an idea where we want to place the wells. And if you go for unconventional reservoirs as well, if you're going to go for unconventional reservoirs, we need to design, you see here in the bottom, how many fractures we're going to have in this fracture reservoir, how many hydraulic fractures you can count, and the position of those fractures. Okay? So that's basically what I'm interested in. And coming up with this, this idea of flow reservoir simulation for this particular problems is a hard job. Right? So let me talk mostly what we've been doing on the fast proxy for reservoir simulation using machine learning techniques. So as I mentioned, reservoir simulation, it is hard, right? And we want to come up with a proxy for that purpose so that we can fit into this closed loop reservoir management, right? We looked at many things in the past few years. Going from the fine scale simulation, how we can get better, faster simulation, all the way to data-driven models. Okay, and of course, there's always a trade-off between computational speed and model fidelity. Okay? So what we looked at, the most was this middle class here, which is a reduced order modeling, which is basically trying to come up with a representation of your simulator, right? Which can be, the output can be approximately equal the input. So we are trying to come up with all this machinery here that no matter what we do with the well controls, we always get the same type of approximation. What I mean by prediction here, it is basically, we are trying to predict what will be the flow, this Q here, of our model, right? So you are trying to inject something into the reservoir, you're trying to produce something else. So we want to optimize how much you're actually producing out of this reservoir. Okay. So let me just briefly talk a little bit about what's a reservoir simulation. It is basically accounting for flow into the porous media. And you involve all this petrophysical information, fluid flow information, fluid physics, geological rock properties, but basically all boils down to an equation, and that's familiar to many other domains, which is a conservation equation that involves here on the left-hand side a flux across your control volume, sources and sinks, and here as well, that's particular for porous media, accumulation inside the control volume related to the compressibility of the fluid and the rock. Okay, so if you account for that, that's basically what reservoir simulation is. And as you can see here, we're trying to control what is the wells, so how much you're injecting in some of these injector wells, how much you're producing in some of these producer wells, and we call these controls here. It can come as a form of a flow, or can come as a form of a pressure control. And the solution here, we can look at the solution in this particular way that we can have what we call states, and basically we look at a solution by actually determining what is the pressure of a particular phase, right? Gas, oil, and water, and what is the saturation of that particular phase, which means that what is the fraction of that particular phase into the reservoir. Okay, so those are the states that we are trying to determine out of this equation. And as far as the output goes, right, this is what we're trying to control. But what we're trying to observe, and what we're actually trying to get out of this reservoir is actually how much oil and how much water, how much gas we're actually producing. Okay, so that's our output. In general, no, these states are large. We're talking about here millions to billions of states. So of course, this depends upon how you're discretizing this PDE here, right? But usually states are really large, right? And the output usually is given by a, I would say semi-empirical relationship here, which is given by, if you can reconstruct the state here, this pressure, we can actually determine what's going to be the output of this well, which is not ideal, right? And that's basically what we like to tackle with our machine learning architecture. We want to, based upon how we are actually controlling the reservoir, we want to predict basically what is this Q here without having to go all the way through that notion of a state, which is still not there yet. But let me show what we have. Okay, so as far as the, if you pose this problem as in a system framework, right, we can get a discretized PDE here and linearize that partial differential equation, and you get a time varying system like that. And what we like to do, it is to come up with those proxy models that can determine what's this ABCD based upon input output, right? It's basically a system identification perspective from a systems theory, right? However, building those matrices, it is difficult, right? We need to access the simulator. We need to get, to linearize this equation, we need to get the Jacobians, to get the states. We need to store them. Then, so which means that we need to come up with something that it's an easy fix for this large scale problem. And this is what's called model, that I call model reduction. So let me just show one technique that we use. There are many, many techniques. But let me just pose this as this trajectory piecewise linearizations type of model reduction. And basically what we do, we run one pass of at least one full-scale reservoir simulation, and we store what's going to be the states, right? The pressures and saturations in offline, so a whole bunch of training in that sense. And then when we go and simulate the proxy model, we have the linearized system that I showed before. We just basically look it up. What is the state that is closer to the one that we are trying to get, and we can predict what is the next state based upon what has been saved already. Okay, and that's basically using that equation right here. That is just an application of that linearized system by looking at what is the closest state from the one that I have already saved. Okay, so that's very nice. People have already done that, but that's still a large-scale problem because all these quantities here, which is the flux, which related to the flux in that PDE, the accumulations and the wells, they're still in the large-scale state, right? We can operate on that by looking at model reduction techniques. In particular, we can just take a proper orthogonal decomposition approach, or in many other fields, a PCA approach, which is basically we look for this transformation here that take all this large-scale state into a much smaller state that we call Z, right? And we're looking for this phi here, which basically can take up from the left singular values of left singular vectors of this SVD. Okay? So if you do that, we can now operate on this Z here, which is a much more reduced space, right? So that's what we call model reduction in that sense. But we're still not got rid of the fact that we need to store many, many things into the process, right? And that comes the idea of using our machine learning techniques, or that I'm going to show to you in the next few slides. Okay, so just a recap. We went from this large-scale system to this small-scale system by just looking at this TPWL type of thing. There are other techniques that we used in the past. I'm not going to talk about that. But again, what is our hypothesis? It is to come up with this reduced form AR, BR, CR, DR based upon Y and U. Okay, so what we are using then? So we looked up some literature. And there is this paper here on that was published a few years ago, and that's basically an idea of using a model and learn from a encoder decoder type of thing that you can based upon a state, you can come up with your ABCD. So I'm not. So basically, the paper talks about how you can do that. Let me just show the modifications and what we are actually thinking about for our problem. Okay. All right. So basically, the question is how you actually. I mean, this. If you were, just thinking about input output without the physics in it, that would be a great problem, right? That we are done, but we need to incorporate somehow the idea and the notion that we have a porous media, right? So how we do that? We do this by looking at how we actually train that that architecture. Okay. Right now, what we are doing, we are looking at inputting the states that we already solved. If you recall, we are in this TPWL mode. We run a reservoir simulator. We have those states already, so we can go to that training right here, right, with that particular states and particular times that we use for training. Right? We can operate a encoder decoder type of thing and reconstruct what is the estimated state and reconstruct what is the estimated next time state. Okay, and by means of those loss functions. Right? So the question is, one, what is inside this encoder decoder? And they are basically compositions of encoding blocks, residual convolution blocks, and dense layers. And I can talk a little bit more later on if I have time what is exactly inside of those. Right? But basically, if you operate on this encoder decoder type of thing, you get your AB form. Right? We can estimate the state. Right? However, how do you actually incorporate this porous media flow? Right? We need to think about how we do that, and how we do that is basically by looking at reconstruction of those three loss functions here. Right? There's a paper, last year that they used exactly coming from the previous paper that I showed. They used for porous media the notion of flux. Here we want to train this encoder decoder in such a way that we keep the in some ways the material balance out of the system. Okay, the material balance of the system. Okay, and that's basically operating on these loss functions here. Okay. However, if you look at the paper, they're actually only estimating what is the next state. The next state. And as I mentioned to you, the output is actually given by the Pisman equation, which is not ideal. Okay? So what we are proposing here, it is a little bit a new architecture to that, in the sense that, first of all, we are, since we like to come up with the oil and water and gas independently as far as the optimization goes, our physical loss functions, they involved multi-phase flow. Okay, they involve multi-phase flow in that sense, and that's accounting for every phase, the conservation of every phase into every particular time step. Okay, so that's one, and the change of our architecture as well. We are actually training now with and let me show the next slide.
Hey, Eduardo, you've got 5 minutes left, including for your Q&A.
Yes, I'm one more slide. Thank you. So, and then we are going through this process here of coming up with another block that we actually outputting. Remember that C and D. So we are outputting that C and D, and we are actually predicting the output of the system by just looking at a little bit of a transformation of that architecture. Okay, so that's basically what we have. Let me just show one example here. We have a wells attached to the particular reservoir. We're trying to control those wells, and basically we run a simulator with those controls with a particular rates, with particular pressures, just for getting the state out of it. My student Emilio trained this into the HPRC. Some information here that's on the slides, and basically what we looked at Let me just show quickly here. We get a, no, if you look at proposition 3 against proposition 1 with no output, right? We are doing a little bit better than estimating the output just based upon this transformation of the architecture. Okay, so you can look at oil rate, water rate, and the pressure in the particular well. Okay, what we'd like to do next, it is to expand this upon to a lot more uncertainty and come up with something that we actually incorporate uncertainty as well, which is the reservoir characterization part that I showed in the previous slide. Okay, so just a conclusion here. There are lots of open questions, which architectures to use. What's the best way of training? There's not, Emilio spent a lot of time on the training portion. We don't know how to train that, to be honest. How do you actually incorporate a lot more on the geophysical insight, right? Especially if you have hydraulic fractures with the geomechanics and so forth. Okay, of course, we can borrow ideas from scientific machine learning, especially the ones here coming from other areas. Okay, and definitely my consensus so far, there is not yet a push button approach, right? It's all iterative process, and which will make things a little harder, at least from the areas that I'm coming from, that people have a reservoir simulator at their hand, and they just can push the button and wait if they can afford to wait and get the solution. Okay, so I'll be open for collaboration ideas, anything that you guys want to add, and any questions that you guys want to add. Thank you.
Well, thanks very much, Eduardo. So for any questions, please feel free either to put them in the chat or ask them directly over audio.
So Eduardo, that's a very nice talk. So how sensitive is your approach to the linearization? And is there a way to do this without having to linearize?
Yes, that's a good question. Yes and no, right? The linearization is actually a part of that, the architecture of this TPWL, which, I mean, you already linearize the system anyway, right? If you go to a reservoir simulator, every time step you already linearize in the system, right? Through a Newton approach, right? Which it is, in that sense, it is not a big deal, because you're already, the philosophy here is that, at least for now, we are using a reservoir simulator to begin with, right? We are using a fine scale reservoir simulator to come up with the states, right? Which is not ideal yet, right? But the linearization now, it is already there into the reservoir simulator. We are just outputting the state, which means that we are believing that the training or the architecture is not sensitive to the linearization per se.
Okay, thanks.
Any other questions?
Yeah, we had another question which I sent me on a private channel, but I asked the questioner to rebroadcast it to the public channel, but I'll read it out anyway. Isn't the latent code much more sensitive to parametric variations? Oh, there you see it.
Okay.
In the public.
So isn't the latent code Z much more sensitive to parametric variations when you utilize an autoencoder than going through? Yes. Yes, that's probably yes, right? We haven't really experimented too much with, but the problem with the POD is, we'd like eventually to go from input to output. We want to have an architecture that takes up production data out of the reservoir and come up with possibly with a prediction of the output of the reservoir without having to translate this into state. Okay, and of course we already done that with the model reduction itself. And if you just look at POD, which basically you just do an SVD of the states, you are guaranteed. I mean, this is much more robust, right? You may play with a little bit of how many POD bases you want to have, but in the end, yes, it's very insensitive to whatever you do into the system, right? But eventually, we want to come up with an architecture that doesn't translate into states.
Okay, thanks. Thanks, Eduardo, and thanks everyone for your questions. So let's move on to our next talk.